Hey everyone, and welcome. Today, we're going to tackle a huge question. How do we get the messy, complicated world we live in into the clean, perfect world of a computer? We're building that bridge from reality to code. Okay, let's get into it.
So let's just start with a kind of funny question. Why do computers hate reality? I know, it sounds weird, right? But seriously, there's this fundamental clash between the world we actually experience and the world a computer needs to get anything done. And, solving this problem, well, that's the first step in all of computing.
And here's the deal. The world we live in is analog. Just think of a sound wave. It doesn't just jump from quiet to loud. It flows smoothly, continuously, through literally an infinite number of points in between. It's messy. But computers, oh, they crave a digital world. They need things to be discrete, certain, clean. They can't do kinda. They need a hard yes or a no, a one or a zero. No in between.
To really get our heads around how we make this jump from the analog world to the digital one, we're going to use a really simple but honestly a super powerful analogy: the difference between a smooth ramp and a set of stairs.
Just picture it. An analog signal is like a ramp. You can be anywhere on it, at any height. 5.2 feet, 5.23 feet, 5.23415 feet. It's infinite, and it's almost impossible to measure perfectly. A digital signal, though, that's a staircase. You're either on step 1 or you're on step 2. There is no step 1.5. It's totally clear, totally defined. So how do we get from that ramp to the staircase? Well, this is where a little piece of tech magic comes in. It's a critical component called an analog to digital converter, or ADC for short. Its whole job is to look at your exact position on that smooth analog ramp and then basically force you onto the closest digital stair. It takes the infinite and makes it finite. Pretty cool, right? Now, the quality of this whole process really depends on how many stairs we decide to build. We call this concept bit depth. So a 1-bit system, that's as basic as it gets. It's like a staircase with only 2 levels: a ground floor, which we'll call 0, and a first floor, which we'll call 1. Super simple, but not very precise. Anything below a certain point is a 0, anything above is a 1. That's it. But what happens when we add more bits? What if we increase that bit depth? Well, a 4-bit system gives us 2 to the power of 4, or 16 distinct levels. Suddenly, our staircase has 16 much smaller steps instead of just 2 big ones. And this lets us create a way more accurate digital version of that original smooth ramp. The more steps, the higher the bit depth, the closer we get to capturing reality. So here's the absolute key takeaway on this. There are 2 parts to making this happen. What we've been talking about with all the stairs, that's called quantization. That's when you chop up the signal vertically by its strength or amplitude. The other part is called sampling. That's when you chop it up horizontally, measuring it at set points in time. You put them together, and that's how you turn a smooth wave into digital data. Okay, so now we get how information gets into a computer. Let's switch gears and look at the computer itself. And to do that, we have to make this really important distinction between a machine's design and how it's actually put together. And for this, we're going to use the one and only Iron Man suit as our guide.
So think about it. When we talk about Iron Man, what are we really talking about? Are we talking about what the suit can do? Fly, shoot lasers, all its cool functions? Or are we talking about the actual nuts and bolts inside? The wiring, the power source, the specific stuff Tony Stark used in his workshop? See? They're 2 totally different things.
And that, right there, is the difference between computer architecture and computer organization. Architecture is the suit itself. It's what it does. Can it fly? Does it have repulsor rays? This is what the programmer sees, stuff like the instruction set. But organization, that's Tony's workshop. It's how it's built. That's the engineer's view, all about circuit design and memory wiring. One is the what, and the other is the how. Okay, so keeping that difference in mind, let's take a peek inside the workshop of a real computer. We're going under the hood to see the core parts that make up pretty much every computer ever, all based on this classic design called the von Neumann architecture. At its heart, a computer really just has 3 main parts. First up, you've got the CPU, that's the brain doing all the heavy lifting. Then there's the memory, which is like a giant warehouse storing everything. And finally, you have the system bus, which is the superhighway that connects it all together. So let's zoom in on that brain, the CPU. It's got its own little team working inside. You've got the registers, which are kind of like the CPU's hands, holding on to whatever data it's working on right now. You've got the ALU, or arithmetic logic unit. That's the calculator doing all the math. And then there's the control unit, who is like the conductor of an orchestra, telling everyone what to do and when to do it. And what about that highway connecting everything, the system bus? Well, it's not just one road. It's more like a multi-lane superhighway. You've got the address bus, and that lane's job is to say where the data needs to go. Then you have the data bus, which is the lane that actually carries the data. And finally, you've got the control bus, and that lane carries the commands, telling everything what to do with that data.
So we've gone deep into the how of computers. But let's talk about the why. I mean, why does any of this really matter? Because understanding these foundations, from how a sound wave becomes a number to how a CPU is organized, unlocks some of the coolest and most in-demand careers in tech. Seriously, this stuff isn't just theory, it's a roadmap to a real job. For example, if you love how hardware and software meet, you could work in embedded systems at a place like Bosch, writing the code inside our cars and appliances. If you're obsessed with making things faster and more efficient, you could be a systems engineer at Google or Microsoft. Or if you want to be on the absolute cutting edge, you could use this exact knowledge to build high-performance AI models at a company like NVIDIA.
Okay, let's do a quick knowledge check. Imagine you're working with a 1-bit ADC. Its voltage range is 0 to plus 5 volts. So what's the threshold for it to switch between a 0 and a 1? Yep, you got it. It's right in the middle, plus 2.5 volts. Anything below that is a 0, anything above is a 1. Simple as that. All right, next one. Thinking back to our Iron Man suit, is a computer's instruction set, that's the list of all the commands it understands, part of its architecture or its organization? It's architecture, because it defines what the computer can do, which is what the programmer actually sees and interacts with. Okay, let's get even more fundamental. Deep inside that ALU, the CPU's calculator, what's the name of the basic circuit that just adds two simple bits together? That's a half adder. It's one of the absolute most basic building blocks of all computation. All right, last one. Let's bring it all back home to something you use every single day. Music. You see two MP3 files. One is 96 kilobits per second. The other is 320 kilobits per second. Which one is going to sound better? Of course, it's the 320 kilobits per second file. It has a higher bitrate, which means it used more stairs and took more measurements to create a much more detailed, faithful copy of the original analog sound. So, we've gone all the way from the messy analog world to the clean logic inside a CPU. We've seen how reality gets turned into numbers and how those numbers get processed by a machine built on some really simple, elegant ideas. The foundation is laid. So, the only question left is, what are you going to build on it? Thanks for joining me.